Section 1.7 of Chapter 1, Additional Experimental Quantities, the first one of which is temperature, the degree of hotness of an object. So, as we discussed in class, you should be aware of how to convert between degrees Celsius and degrees Fahrenheit, and from degrees Celsius into Kelvin, and from Fahrenheit into Kelvin, so on and so forth. So, just some interesting numbers here. So the first one is, you can see that the freezing point of water in Celsius is 0 degrees, and in Fahrenheit it's 32, whereas in Kelvin it's 273. And then if you go all the way up to the boiling point of water in Celsius, you can see that it's 100 degrees Celsius, but in Kelvin it's 373 Kelvin. So that tells you that to convert any temperature from Celsius into Kelvin, I just need to add 273 to it. The calculation to convert from Celsius to Fahrenheit and vice versa is a little more complex. So these are formulas that you will be responsible for the first exam, and you should know how to apply both of these formulas. And here's a couple of quick questions that we looked at in class that you could try again. So remember, you need to have these formulas memorized, and I also posted a YouTube video that deals with temperature conversions and significant figures. So the Kelvin temperature scale, again, to convert from degrees Celsius into Kelvin, you just need to add 273. Whether you add 273 or 273.15, well, that depends really with the number of significant figures that you're starting with in your Celsius number. Energy is defined as the ability to do work. So a couple of types of energy: kinetic energy or potential energy. Kinetic energy is the study of, the energy of motion, whereas potential energy is the energy of position, so that's what we call stored energy sometimes. Energy can also be categorized according to form, and there are several different forms of energy here: heat energy, light energy, mechanical, chemical, and electrical. Some important characteristics of energy. This one might not be intuitive, but energy cannot be created or destroyed. We can't create energy and we can't destroy it. Energy can be converted from one form to another, but we cannot create or destroy it. Energy conversion always occurs with less than 100% efficiency. For example, when you burn gasoline in your car, some of it is used as mechanical energy, which helps propel your car and yourself down the road or down the highway, but a lot of it is lost as heat. So all chemical reactions involve either a gain or a loss of energy. The basic units of energy are either the calorie or the joule, is what we most commonly use in Chemistry 101. And you can see here that 1 calorie, and it's important that I note that this is with a small c, 1 calorie is equal to 4.184 joules. A kilocalorie, which is, we put K in front of that, so K stands for kilo, that's 1,000 calories. So the kilocalorie is also known as the large calorie, the big C. This is the same as food calories. So if I sum it up, I can say that 1,000 small calories is equal to 1 kilocalorie, and a kilocalorie and a big C calorie, those are synonymous. Those are the same thing. So if you go to the grocery store and you look at a box of cookies or a can of soup, and it tells you how many calories per serving there is, that is given to you in big C calories. And again, for every 1 big C calorie, you get 1,000 small calories. And the calorie is simply defined as the amount of heat energy that it takes to heat up 1 gram of water by 1 degree Celsius. So if you're astute, you can probably figure out that 1 big calorie is the amount of energy it would take to heat up 1 kilogram or 1,000 grams of water by 1 degree Celsius. Concentration. Concentration is simply the number of particles of a substance, or the mass of those particles that are contained in a specified volume. We can use this, often used to represent mixtures of different substances. Here's just a few examples, like the concentration of oxygen in air, for example. But we use the word concentration in our everyday vernacular all the time. A good example would be if you were to make something like Kool-Aid or Gatorade, you could say, oh, this is too concentrated, or it is not concentrated enough. So if it's too concentrated, it tells you there are too many particles. There's too much sugar. per unit volume. If you say it's not concentrated enough, you would basically be telling somebody there's very little flavor, so there's not as many particles. And we're going to talk about how to quantify that as well in this class, how to quantify concentration. But a couple of the last concepts that we have to look at in section 1.7 are both density and specific gravity. Density is simply the ratio of mass to volume. You may have seen this formula somewhere before. D is equal to m over v, which is density is equal to mass over volume. It is an intensive property, so it's intensive to a substance. So whether you have 1,000 kilograms of, let's say, lead or 1 gram of lead, it's going to have the same density. If you have 1,000 liters of water versus 1 liter of water, the density will not change. So that means it's an intensive property. It can be used to characterize a substance, as each substance has a unique density. For example, gold is a metal that would have a much higher density than, say, something like air. Units for density can include grams per milliliter, grams per centimeter cubed, and you might see this sometime in the healthcare profession, is grams per cc. Cc simply means cubic centimeter, so it's the same thing, but all of those can be used. So you are responsible for knowing the formula density is equal to mass over volume. D equals m over v. Here's a really interesting picture which shows 4 different substances in this beaker, and you can kind of compare the densities of all 4 of these. You can see that the liquid mercury must be the most dense because it's on the bottom, and you generally don't think of a metal or an alloy, like brass. You don't think of that as floating, but the brass must be less dense than the mercury, and therefore it rests on top of the mercury or it floats in it. Water, you can see that the brass nut sinks in water because brass is going to have a higher density than water. And then you have cork, which is actually a type of wood, which, as you know, if you've ever picked up a cork before, it's very light per unit volume, so it is not very dense. So since it has such a low density, it floats in the water. It's kind of an interesting picture that helps us relate density of these 4 substances. So you can see that cork is the least dense, water comes next, brass would come after water, and then you can see that liquid mercury would be the most dense. If you look at table 1.4, it just shows you the densities of some common materials. Something that everybody's probably familiar with is the density of water, which is 1 gram per milliliter at 4 degrees Celsius. You can see that it changes slightly when you warm it up once you get up to 20 degrees Celsius. If you look at wood, now it's listing a bunch of different types of wood, and you can see that there's a range of densities, but generally speaking, wood is quite a bit less dense than water. Therefore, wood should float in water. You can see that air has a really, really low density. I mean, you compare that to 1.000, we have 0.00129 at 0 degrees Celsius. You can see the air is not very dense. Anyhow, we could spend a lot of time looking on this, and this is something that might be interesting to spend some time studying to some degree. All right, let's move on from there. How do you calculate density? Here's an example. It says here a 2 centimeter cube sample of aluminum is found to weigh 5.40 grams. Calculate the density. Well, I mean, you can go through all of this planning here, planning the trip, but the best way to do this, or probably one of the simpler ways, is just to memorize the formula, which is D is equal to m over v. You can see that the mass is 5.40 grams, so we could say that's our mass, so we can plug that in, 5.40 grams. You can see that our volume, so now we're looking for V, is 2.00 centimeters cubed, so that's our volume, 2.00 centimeters cubed. So when we divide 5.40 by 5.40 grams by 2.00 centimeters cubed, well, let's just move down. I have the calculations all done here. You can see that you get 2.70 grams per centimeter cube. And since a centimeter cube is equal to a milliliter, you could also express it as 2.70 grams per milliliter. It doesn't matter which one you use. They're both the same. Okay, they both mean the exact same thing. So there's an example of a density calculation. Here's another one here. It says calculate the volume. So we're looking for volume of a liquid in milliliters that has a density, so here's our density, of 1.20 grams per milliliter and has a mass of 5.00 grams. So we use the same formula. Density is equal to mass over volume, but using algebra we can rearrange the formula to solve for volume. So we can say that volume is equal to mass divided by density. So there's the formula that I'll need. So I can simply plug the numbers for mass and density into my formula, which I've done here on the next page. And you can see that 5 grams basically divided by 1.20 grams per milliliter gives you 4.17 milliliters. And the last concept is, after the density calculations, which you can take a look at on your own time, it's a good idea to try all three of these, is the concept of specific gravity, which is, for Chemistry 101, we deal with specific gravity relative to water. So values of density are often related to a standard. In our class, we're mostly going to be talking about relating it to water at 4 degrees Celsius. And if you remember from the table that we looked at, that water at 4 degrees Celsius, its density, so if I put the density of H2O, is equal to 1.000 grams per milliliter at 4 degrees Celsius. So specific gravity is a unitless term because the two terms cancel. The two units cancel out, the grams per milliliter and grams per milliliter cancel out. It's often used in the health industry to test urine and blood samples, and that's something that we'll talk about a little bit more in class. But you will be responsible for memorizing this formula as well and knowing how to apply it. I don't like to use the words simple and chemistry in the same sentence, but I'd say this is one of the easier formulas that we look at, because basically what you're going to be doing is taking the density of whatever object we're looking at and dividing it by the density of water, usually at 4 degrees Celsius, which is 1. So most people are able to take a number and divide it by 1 in their head. Alright, so I hope you find this video useful.